All right, well, then I guess without further ado, we are welcoming Nguyen, who's going to talk us about trustworthy and explainable AI. Please.
Thank you, Professor Bologna. Yes. Okay, so thank you, Professor Shah and the search committee for inviting me here to give this wonderful talk at USCF. So before we start, I would like to briefly introduce myself and where I end up in this journey. So I'm originally from Vietnam. I did a bachelor in computer science in Thailand at the English-speaking institution. And then I went to Singapore. I worked as a software engineer for a few companies and spent most time 2 years at Bosch, the German company famous for power tools. And now they do a lot of things, including self-driving cars. Before I followed my wife to the US. And then there I had spent some time at Apple as a research intern in Uber AI Labs before I joined Auburn. So at Bosch, I was leading a few efforts, and mostly in front-end programming. One of the efforts was this tool called Visual Rules. It's an editor for business executives, so that now if the business executive they want to change, for example, a certain threshold for their finance product, they would just go into this editor and then just make a change in the logic, and then automatically the system will render into the software. The software will behave as an SaaS, software as a service. So there's no need for asking programmers to make implementation anymore. I was in charge of the interface here, which is like, very, very interesting. And this inspired my later work in the XAI. And how can we achieve this in the XAI? So this is the software engineering part, and then I went to U Wyoming and did a master in virtual reality. I know some of our faculty work in human factors in HCI, like Joseph Laviola here. So my work is very inspired by Joseph Laviola and Doug Bowman. Here I built an interface for virtual environment. It accidentally got a paper at Virtual Reality, it's top conference in the field, and even a patent, and a lot of interest to commercialize the product. This is all before the PhD. Then 2014, I decided whether should I go to one of the FANG company to be a software engineer or just continue. And then that's where I met Jeff Nguyen, who persuaded me to join his journey. It's really wonderful, and I did a lot of work in trustworthy and explainable AI. I only most of these I don't have time to share with you. They're really cool, but I only share about this work plus the more recent one I did at Auburn. So I did my PhD completed in 2017, and then I started the professor job at Auburn, and now it has been close to 6 years. So in the AI area, I classify myself as an ML person working in applications of CV and NLP. I was lucky to be recognized by different awards at the top CVPR and then evolutionary computation venues for papers, and then videos, and also a lot of works on the media. Okay, so let's start. So I just need to probably there's no need to convince everyone that AI is everywhere. It's everywhere. They are knowing what we are doing, and it's hard to differentiate whether we are slaves to AI or the AI are actually slaves to humans. So this time, I think it's equal. So the one thing, this is the projection from PricewaterhouseCoopers. These are the jobs that will be increased due to the AI. And these are the jobs sectors that will be decreased due to the AI. So you can see here manufacturing, transportation, and public administration. So let's take an example. So in transportation, so this is where you expect that, for example, self-driving should be solved very early, right? This is an Elon Musk prediction in 2019, where by the end of 2019, we have featured complete full self-driving cars. However, 2 years after this announcement, FSD9 is still having trouble recognizing the moon. It thinks here in this case the moon is the yellow light. So what are the problems here? You can see two problems. One is the visual perception problem, where it cannot recognize the moon. But the second problem is that there's a temporal pattern that is not being recognized here. How come what kind of traffic system that has like the yellow light every few seconds, right? So this is not right. And not only this is one single cherry pick problem, but there are tons of other problems as of like less than 2 years ago with Tesla FSD9, and this is a leading company in autonomous vehicles. So as an evidence, like two passenger unfortunately trusted the car and then sit in the back seat, and they just let the car drive all by itself, and then it crashed and then killed both persons. This is unfortunate, but it's also like a hard proof that the AI is not there yet to drive all by itself. So now this is transportation. Now if you go to public admin and defense, so you would think that surveillance camera right now is everywhere, and the AI should be watching them. And there have been some efforts from Professor Shah and the UCF to implement AI into tracking people. So, however, this has been done also in many states to help the police to find the suspects, right? However, there are several incidents of false accusations. So because AI sees some person thinking the suspect, and the police will go after them immediately. So there's no questions. However, there are men from Michigan, Wisconsin, Detroit, Illinois, so everywhere that are falsely accused just because of the Face ID system said so. So this is a strong motivation for me to continue in this wonderful journey of trustworthy and explainable AI, which I will share with you here. And most of the work is done at Auburn. So first is, I want to build AIs that are accurate in edge cases. That's what defines the trustworthy, because robustness has a different meaning depending on the setup and also the common cases. So I want the AI alone to make the correct decision, even when the input is rare, is edge case. So I want to build AI such that it will maximize, when you feed the input to the AI and the humans, it will empower the human to make better decisions. So this is a human AI team accuracy. So better than AI alone and a human alone. And lastly, I want to build AIs that humans can debug and can edit. So there are many things you can debug and edit, but the one specific thing you want is a decision-making process. So AI could make decision by itself, but or humans, depending on the setup. But what is novelty here compared to the prior work is that there should be a two-way arrow between AI and humans. So humans should be able to debug and also edit the AI decision-making process, and not just AI giving the information to the humans. Okay, so the part one of the talk, accurate in edge cases. So let's start from the classic example here. This is the example I have been given in many talks. So if you have a typical way set up in supervised learning is that you get a lot of data and you have to label them. So right now there are many ways to harvest a label from the internet, but let's say you have a training set of school bus and you train the school bus detector, right? So at the test time, you will take the image, the IID test sample from the test set, the same distribution as the training, and then feed it to the AI. After you train it well, it will tell you this is a school bus, so nothing is wrong. So fantastic. So one attempt to, if the model is already working well, there's a desire to reverse engineer the process to see what's going on. What do the model think is a school bus, right? So one way we did is we use a CPPN, which is image generator, where we evolve this image generator. We basically train them, but also train not just the weight, but also the topology, the network connectivity. So we train this image generator such that it will generate an image such that if you push it through the AI, it will maximize the school bus confidence score. And we use two objectives, diversity and confidence score. So here we use evolutionary algorithms called MapElite. It's multi-objective black box optimization that will maintain the population in these two criteria. And if you repeat this process for 5,000 iteration with population size of about 400, so it will end up with images that looks like this, such that the image classifier would think this is 99% school bus. And not only that, there are many other classes. For example, penguin. So this is a Google. This is Alex and also Google Inception thing. This is penguin, starfish, baseball, electric guitar, and so on. So this is really interesting because this is happening to the state-of-the-art model. Now, if you, and the reason that we get this regular pattern is because we use this image generator, which imposes strong prior to the images. If you remove this generator and just trying to find the pixel that maximize this confidence score, you would end up with images that looks like this. So they're completely white noise. However, they maximize the model confidence score. What is really interesting here is not just images itself, it's generalization. So these are the 3 images that we publish in among the images we publish in our paper. And Dalip Josh, who is the CEO and founder of Vicarious, AI startup in the Silicon Valley, working on AGI. So he was so fascinated by the work, and he took this picture using his phone, which is running another AI, as an image classifier based on ImageNet. So interestingly, the model also thinks this is a digital clock, green snake, and stethoscope. Here, although you see images coming from different angle and then the quality, that image is much blurrier than the original we have. However, the model on his phone is also misclassified to exactly the same label. Hey, Professor Wang, the same label. So this shows that the many models of a different architecture but trained on the same image data set share like 25% of vulnerability. So you can imagine this will translate into the future where self-driving cars would see a passenger wearing this black and yellow stripe and would think this is a school bus. So this is one of the first work we did in this area, and it pioneering in this area, and it attracted a lot of community and also the public attention.
So this is a bit different than this FGSM attack
Right. So the difference from Shagadi's work is that he started from a real image. We started from a random image. We are after him like 6 months, but we are aware of his work before. For us, we start from a random image, I guess. And we have some prior over the image, but the adversarial attack, normally they don't have impose any prior, just manipulate the pixel by itself. Right, but we work here in this space.
So in statistics, this is like a type 1 and type 2.
Type 2. Yes. Yes. And then one day, even Gary Marcus, who is professor at NYU, he even printed out one of the images we generated. The image says, his shirt says that, don't worry, killer robots, I'm really a starfish, and show it to Larry Page on the right, that's Google. So how do you train AIs to recognize this is a starfish? It sounds like really a silly question, right? If you have a training set, maybe the easiest thing to do is to just add them to the training set. This is the fundamental idea behind data augmentation and adversarial training. However, you need to add more and more if other people invent new types of images, like adversarial or fooling images. And there are a flourish of a number of pixel-wise attacks, what they call attacks, basically the different ways to manipulate the pixel to force the model to think in the way they want it to think. However, one recommendation we made in 2019 at CVPR is that there actually no need to manipulate the pixel itself, because most people in this area, they forgot about the threat model. It's not really realistic to go to the camera and try to manipulate the pixel, because in real life, there's so different lighting condition, camera lens, so different extrinsic parameters that you cannot control. So that what is more worrisome is that you don't even need to manipulate the pixel to fool AI. So I have here an image that the Google Inception V3 say this is a school bus. It has a 78% accuracy on 1,000 weight classification. So what we did is we take this scubas and we just rotate it. Oh, it is different than on my computer. Rotate it, and now it's no longer scubas to the AI, same Google net. What we did here is we set up this the chain where we manipulate the objects here. Basically, the function is only manipulate the rotation and the XY coordinate, XYZ coordinates of the object, so 6D, such that if you render it through either OpenGL or the explainable renderer, which I both, into an image that will maximize the classifier prediction. Okay, and you can do a black box backwards or use differential renderer, then you can just do gradient descent. Okay, so in this way you can reveal many adversarial cases. So the model will think this is 0%, like 0% scubas, no scubas at all, these images. Instead, the model will think this is a chain, scabbard, amphibian, and forklift. So what we think, what is really interesting here is that if you plot this space that where, okay, we have, this is changing in pitch, and this is the changing in the roll. So at this point, the object looks like this and is correctly classified as a fire truck. However, if we just rotate it a bit, it will become something else, and the fire truck probability goes down almost to 0, and this will classify into something else. So it's the red, it's wrong. So all the black areas are where the model gets it wrong. The top one label is wrong. So you can see that only 3% of the poses here, 60 pose, 3D rotation and 3D XYZ, are correctly classified by the Google Inception network. And you don't have to you can use our tool we publish online to try to play with it and see the vulnerability, but you also can just place an object on the ground and take a photo. You will see pages like this. This is umbrella, but classified wrongly into many classes, just by changing the rotation, the point of view. So this is a fundamental problem to vision, at least 3 to 4 years ago. So how do you even solve this? Again, the obvious way is to add these images to the training set, and then you try what is going on, right? So we actually did that. What we did is we have here what we call training set objects. So these are objects, we first take them and then render them into different poses and then put them in the training set. And this is held out objects where we do not let the model see it during the training, but we use them in the test time. Similarly, for other objects we have 30 objects in total. We have a pair of training set and held out objects, so the model never see these images rendered from these objects before, 3D objects before. So now if you just train on real data and on just training set objects, it's very easy to fool this. So 99% error rate if you try to target the model on certain class. It's very easy. This is untargeted attack. Just switch a label to something wrong. It's very easy. However, if you do adversarial training in a way that you train on both real and adversarial, so you train on different poses, like adversarial poses of this, and then of this. So you are able to reduce error rate down significantly to 6%, and you test them again. However, on held out objects, it helps a little bit, but it's still a large amount of error if you test them again on the held out objects. So the point here is that if you just try to solve this problem in the 2D space, it does not work. At least does not scale. Of course, if you just consider the image to be small, and there are this many images that 8-bit images that you have to add to the training set if you want to cover all the images possible. So it does not sound like a scalable type of work if you only rely on images and adversarial and training. There should be some different secret sauce to add to the equation. So one idea we have pursued recently is the following. is you want to build a system 2 kind of model in Daniel Kahneman's definition. System 1 is something you recognize within 200 milliseconds. System 2 is something you need to, the process you need to think over and over before making decision, let's say buying a house or solving arithmetic problems. So we want to build a system that first explain and then decide. So there must be a constraint on the explanation first, and then it can make a prediction. And then the second item of the equation is we want to harness external knowledge base to make informed decision. We do not want the model to just use the query plus the weight and then make prediction. Instead, we want to be able to manipulate and control the knowledge base that go into the XAI, and then it generates the explanation. And then finally, from this, it construct or derive the decision. So this is something we propose in the career project, NSF career project. So in the last knowledge paper, this is what we did. We start from the query, and in the training set, we compare the query to 50 training set images, and then we rank them. And then we re-rank them again using the patch-wise similarity. And we take the top 20, like in KNN, top 20 to make predictions. So the majority vote among the top 20 candidates will be used to derive the predicted label. So this is even in grosbeak. And there are 2 ways we find the patch-wise similarity. We try both. One is using optimal transport. So we have first a process of cross-correlation where we find the similarity between 2 images patch-wise, and then highlight to derive this heat map. This is like very similar to cross-attention in transformer. And then from here, we compute the EMD, the earth mover distance, in order to arrive at the cost to transform this image into this image. And from there, we select the top 5 most important patches for this transformation to happen. And then we use that to derive a score, how similar this bird is to this bird, only using 5 patches per image. And the second approach, we use the amortized approach, where we first use a model that called CHM, that is convolutional Hauge matching network. It has been trained to do graph matching. So it finds correspondence between the pairs of images, and then from there we derive the patch-wise similarity score. But again, we constrain it to be only 5 patch comparison.
So in this one, so the first one, so you want to just find how similar 2 images are. Right?
Yes.
That idea. So once you find also the images, then how do you use to do it?
Yeah. So there is a first. There are 2 stages. Stage 1 is ranking using image level feature, the whole image, the global. After you rank them, you know that this is there's a vulnerability, because looking at the whole image is easily full. So you re-rank them. You re-rank the top 50 or top 200, and re-rank them using patch-wise similarity. So it's like a second step. You zoom into the image and then see what are the actual patch-wise similarity, and then re-rank again. After you re-rank, you actually need better performance.
Yeah, so I understand, but what's the big picture? So what do you want to do? So you have a classifier which gives you given a query image, what is class?
What is the classic? I want to do 1000 way classification. Single label.
Yeah.
Yeah.
So like image, right?
The image, yes.
So,
image.
okay, so you will have trend classifier give you this particular image in this class.
Yes.
But then you want to let's apply them to fix them, right? So what's the is that like you're not training the neural network, you have a different approach to do classification?
So maybe we'll go to this. It's easier to see. So I have this is a query image. I want the model to predict 10 among 1000 category.
Yeah.
So now Google, a few years ago, they invented this adversarial attack called adversarial patch, where you just put a patch on the image. It has so high intensity, and then it has an adversarial pixel, such that now the model will think this whole image is a toaster. Okay. You actually take the feature out and then try to compare. These are the nearest in the feature space to this image. So if you only rely on the image level feature, the deep feature, it's going to be full. So this is a problem. The problem we want to solve is that, hey, we should not rely only on the weights of the CNN. Instead, we should carry along a set of prototypes, like what are examples of N and what are examples of toaster. We do KNN, we do K nearest neighbor. So first we do K nearest neighbor in the using image level feature. So we rank them first, and then we re-rank them. It's re-ranking using patch-wise similarity, and then we use it. We achieve the patch-wise. So because we receive only in the 5 patches, so now you can see the model this is a hand because we actually ignore this. We do not allow it to use the whole image.
So then you're not using the CNN image classifier, because you have a different approach to classification based on your sample.
Yes, yes, sir.
Or you are using features.
I still use the same features of CNN. That's no actually trainer in this process.
Yeah.
Just changing the way how the model make decisions.
But that's additional computation.
Additional computation, it's expensive.
And that's like a traditional vision, what we used to do. Find the features and okay.
Yes,
Okay,
yes.
yeah, I got it. Thank you.
But here is the model figure out which patches they should use. And the model should be wrong.
You determine which patches to use. Your method.
There's no human in the loop. There's no human in the loop here.
Oh, okay.
Yes.
Okay.
So how are the relevant patches determined?
Yes, sir. So this is a process called cross correlation. This is basically cross attention in transformer. So if you're not familiar with transformer, it's basically you take each patch here and then it co-attention and compute the similarity between one patch embedding and then the entire image embedding. If you keep doing that, you have the 749. We have 49 numbers. We put it here in the heat map. You do it the other way. Each patch compute the similarity between each patch and each one, and the whole image too. You have 49 numbers. It turns out that actually it works really well. You can select the most relevant one. So from here, you have the weights for each patch already. To compute the optimal distance, you need the weight for each patch. And then the distance between 2 patches is basically just cosine distance. And then from there, you can solve the optimal transform problem. And then you arrive at the cost to transform one image to the other. Based on the cost from each pair, you can re-rank. You can re-rank the KNN. The KNN now has 2 steps. So of course, this optimal transform is, optimization problem affects high diffuse region. So we only re-rank the top 200, not the entire training set, like 1.3 million. The bottom approach is just amortized version of the top, where you have a neural net instead of a optimal transport. So it turns out that if you test it on OOD, the Auburn distribution data set, it improves suddenly all the accuracy with some extent of losing accuracy in the test set, IID test set. And okay, you can counter the problem, for example, adversarial patch, but also you can solve the problem. For example, here, this image is typically classified into parachute because most pixel here dominating this image is a cloudy sky, and it matches the parachute more if you just look at the pixel level. However, if you allow the model to pay attention to only a subset of patches, you will find out that it is actually a goat, an ibex. And you can see now actually how the model makes the prediction using which correspondence. Okay, so the approach is first explain to generate that correspondence and then decide. And the whole thing is transparent because you do not decide first. That's a typical way people do it. Decide first and then try to reverse engineer. What did I do? So this is also have a natural application in phase ID. If you have worked on this problem because you have a gallery is equivalent to a training set or image set, and you try to find this person, identify him. This is extremely hard problem because it's and it involves extremely hard problem because the human may you age, you wear makeups, you wear glasses, so this is typically a ill pose and a zero shot problem. And there's a human in the loop because human needs to make a decision. So this is extremely hard problem. That's why we see many wrong accusations because the Face ID said so. So we also work on this Face ID using a similar technique. So you start from an image, and we render them using style again. Style again allow you to put like different attributes on the image, for example, a glass. And we want to test the model in this way. So if you put a glass on this this girl a photo, and you try to use just the image feature to search, these are our top 5 using state-of-the-art face feature extractor. So it's actually working pretty well. You can find even a person wearing glasses, right? So it has 98% on the test set. So now if you, during the COVID era, people are wearing masks, and how can you identify the person? This is very challenging compared to face detection. So it turns out that if more model will basically sync miserably to 39%. If you just wear a mask with the query, the training set, the gallery is still no mask images. So our approach using something that I have shown you before, but in the Face ID domain, you can improve the accuracy by 10 points without any retraining. So no retraining of the model using exactly the same data, same feature extractor. You just change the way the algorithm works.
What if you do completion first? Like image completion.
Exactly. So we look into this. There maybe should be a baseline here, but the completion will change your identity. It's extremely hard. Yes. It's no more the same person. So at least this one, using the two-state approach, ranking first and re-ranking, it allow you to see, oh, this is how the model. The screen is freezing. How the model make prediction that the first person is the query due to these patches, but it does not use this. So the model is able to filter out the irrelevant or the ill-posed areas of the image. And again, this is a two-stage. First, you use the image level feature to rank, and then you use the EMD patch-wise similarity to re-rank. This is very effective, and it allows the model to first select the feature automatically that are relevant to compare, and then you use it to re-rank. So you can see here when the model, the query wearing glass mask, correctly retrieve the person here and not use this mask area, and then it will ignore this glasses area and just use the mouth area. Profile. And we plug this algorithm to a lot of feature extractor and a different data set. You can see it actually improved for almost all the settings that we tried. So this gives us not
in both of these, you are not talking about computation, right? Comparing the computation with your method or other method.
We have the computation in the appendix. We do have it.
But you will have much more computation.
Exactly. So to be honest, the industry probably will not use this approach because it's too slow. However, if you have a human in the loop, right, and if you are about to arrest someone, then you probably want to use it. But if you don't want to use it for massively looking at like 1 million images on the internet or on the surveillance camera, if you do want to make a decision to accuse someone, then I think you should.
Back to the computation and
this is CVPR 2022, so I don't have exact numbers in my mind, but it's slow for one image. It's like 2 seconds to compare it to 50 milliseconds. Yeah. If you just do one shot, but it's acceptable. It's not like 30 seconds. And this data set mostly has 10,000 images in there. So not a lot, but not like 1 million. Okay, so that's part one. Part two of the talk is I want to talk about how do you build AI that can maximize the human AI team accuracy. So in other words, I want the AIs that can inform the human, such that human will make better decision. Why we need human? Because again, because of this situation where the police needs to make decision and they are wrong because they just follow blindly the AI. So there is a stakeholder in the loop, and he needs to make high-stake decision. And you can see it's not only in this surveillance setup. In Florida, New York State, Wisconsin, there has been in 2016 like use of Compass. This is a model where the AI that take in the profiles and then predict the risk that you will commit the crime again. So this is recidivism. So, and it's actually tend to heavily biased towards the Black people, unfortunately. So the girl here, according to the judge, they have a similar profile to the right, but usually a model will think this is person should be higher risk. So they have been basically mistreated by the AI. And the judge is the one who uses the AI to make decision. So this is recently 2001 where Tesla was sued by Texas cops after like a model, the Tesla Model X, it sees a flashlight of a police car and then it ran into 5 of these officers, seriously injured them. So this lawsuit is still not resolved yet, not concluded yet. But the Tesla basically says that I don't know how the model misbehaved, but you need to read the manual saying that you cannot trust my AI. So basically, nobody knows how to hold anyone accountable at this point. But someone was hurt. There's another case that's where you need to AI to be explainable is at the Trivago, which is a website. It's like Expedia, if you don't know Trivago. It's selling you tours and then the trips. However, when the user chooses the lowest tours, it does not give you the lowest tours. It actually give you the tour of it will actually use a commission to give you the tour, not the lowest price. So it's actually misleading the consumers. However, when ACCC, which is Australian Commission to protect customers, they bring Trivago to the court and then they say that you guys misleading my customers. But nobody knows why, because the model is entirely black box. However, the ACCC has to use XAI to reverse engineer the model of Trivago. And they later figure out that actually the commission is #1 criteria. The price is at best only criteria #2 when they suggest the price. So this cost Trivago 44 million in this lawsuit. So it's very important when it comes to tort litigation. In European Union, there has been this GDPR where they specifically enforce the AI that takes in human data and make decision on human. You need to provide an explanation. In the US, it's not there yet in the regulation, but I predicted it will be soon, given how AI is pervasive these days. So DARPA in 2016 announced this program. This is like right before I started the professor job, so I missed it. So basically, they call for research that helps the soldier to make better decision, like basically more explainable model. But they hope that you can bring the model to have similar test set accuracy, but better explainability. And they define explainability as these 5 criteria. But for me, my research is focused mostly on task performance and how can you correct the model. Okay, so I will give you a brief overview over the existing XAI work to put my work in the context, how it's different. The XAI, it's a lot of work has been done in feature attribution maps. The research question here is phrased as what input feature cost. So when you have an input image, you feed it to CNN, it will classify as 54% matchstick, right? So the feature attribution is trying to ask the question, what input feature caused this prediction? It is after the fact you decide first, and then I will try to reverse engineer what do I think. So the hypothetical result looks like this, where it will localize the input object here, and then it will highlight anything that is for the matchstick decision and anything that is against decision. So basically, you want to come up with the A function that takes in input the model and some hyperparameters and output this heat map. This is like weakly supervised localization task. There has been like dozens and hundreds of papers on this topic, from natural images, people at Oxford, to MRI, to text, to video, and then audio. So everywhere. And then they can be classified into three main types: gradient-based, perturbation-based, and then gradient plus perturbation. So our CPR 2020, we look into the effectiveness of these types of models, types of methods. So the gradient-based is the simplest way to generate these attribution maps, where usually you compute the gradients of the loss of the training with regards to the weights, and you want to update the model, right, doing backpropagation. However, this problem is you backpropagate all the way through the weights and all the way to the image. So if this is input, this is your output gradient image. However, it will look like this for this input image. Okay, for the goblet, it will look like this, and this is for the matchstick image. So what you can see is that how can you even interpret these images, this gradient heat map? What does it tell you about the CNN, right? So one thing you can see is that it just tell you this ratio, like the sensitivity, how sensitive the model is in this area. The small changes in this area would cause large probability change in the output, and that's all. But what you want to see is that it's very interesting that you can just manipulate a pixel here, and that's enough to cause a large change in the prediction. Or here, there's not even overlapping with the sharp at all, and you can change the model prediction. This is like Achilles' heels of a CNN. It's the same as adversarial examples. If you just use this heat map, it does not explain too much. One is because it's noisy, and second is basically a sensitivity analysis. And is it useful to human? That's a question. So the people from like physics or economics, they will use something called perturbation. If you have heard of Shapley values, this is what they do. So the idea is the following: you want to extract the objects from the input image and then try to ask how important is this object, right, with regards to the output decision. So what input causes this output? So what usually you want to do is compute this individual treatment effect. So in this simple case, you would just remove the matchstick and then run it again to the model and then see the prediction, right? So the difference here would tell you how important is this flame, right? So the idea is perfect, nothing is wrong. However, the devil is in the details. So how do you actually select out an object? It's not easy question. It's non-trivial. So one way is you can use patch-wise. So you can mask out a patch and then just slide this patch along the image. So eventually you will construct something like what NYU researchers did here. These heat maps, it tell you the treatment effect for every patch. However, it will have a problem because you don't know what is the ideal patch size. If the object is too small, you will have these artifacts, right? So people at Washington came up with LIME. LIME is a method where you don't rely on the patches, instead of you rely on superpixels. So you divide the image into 50 superpixels and you try to learn the coefficient or the importance weights for each superpixel. So these heat maps show the importance weights, the importance such that if you apply them element-wise onto this perturbed image, you should have a similar prediction score as you input the image to the original classifiers. So basically, they want to learn a classifier that is faithful in the vicinity of the original image. So this is nice, but it will have two different problems. One is it reduces the resolution of the heat maps, and the second is they use grayscale pixels. This is problematic because if you feed these images back to the CNN, they will think it's mostly a jigsaw puzzle or maze or hand of the woods. So this is like our distribution counterfactuals. This is not what humans expect. In economics, people would use Shapley value, and this is recently brought into the computer in AI. However, computing a true Shapley value is intractable, and there are many approximations which also create many different problems. The approach from the Oxford by Vedaldi's group is the following, where you learn this heat map. You learn this heat map by solving this equation. I want to find the smallest minimal region such that if I blur it out, it will minimize the classification score. So I want to find the smallest region. Okay. The problem with this is it will solve the coarse problem because now the heat map is high res, and second, it does not rely on the gray pixel. It will use a blur, which is a reasonable image prior in vision. However, if you pose the problem of searching like optimization, non-convex optimization problem like this case, you will hit another set of problems. Because, for example, when should you stop the algorithm? If you stop at a different time, you will get different results, right? And there are many other cases here, hyperparameters you need to tune. So basically, a lot of existing work, thousands of them, commit this crime, one of these crimes. So first, they are after the fact. They do not probably tell you exactly how the model arrived at the decision. Second is they are having too many hyperparameters that are sensitive to them. For example, changing even the random seed can cause you to have a different explanation. It's very hard to reproduce because they all rely on a specific set of settings, just like a deep learning. If you tune the secret sauce is actually in the appendix, right? It can be misleading because people apply different kind of, like this work by Google, they apply different smoothing prior to the heat maps, and it caused different interpretation to the original one, a completely contrast interpretation. And this is the work we did at Auburn, where, for example, this image is the Jeep, and it's correctly classified if you just rotate it in this way. According to Google Inception, it becomes snow plow. However, if you try to plot the heat map, it does not tell you exactly how this is a snow plow. It still highlights the main object, and this is a snow plow. So there's no idea. So a lot of work in this space where we have to rethink how the community was thinking, and then to actually ground them to the downstream application. In the RIF 21, what we did is we took one of the things we did is we did a human study over more than 300 people, where we asked them the following. If I give you a confidence score and I give you this image, the AI, the state of the art say this is lorikeet. Can you confirm this is lorikeet or not? Say yes or no. This is a binary classification problem for human. Because if you give you 1,000 labels, they cannot choose. Okay. So the second setting, the treatment here is that I give you confidence and the heat map tell me, and the input image tell me lorikeet or not. Okay. And I will use different state of the art heat maps. The third setting is that input image, the confidence, and also these three supporting images in the same class as the lorikeet, the model predictor. Tell me this is the lorikeet or not. Okay. So what we found is that normally one metric in the XAI is that they trying to quantify the heat map goodness by using this weakly supervised object localization. If you overlap more with the ground truth human annotation, I deem that you have better heat maps. However, we find that there's no strong correlation between the object localization and the human accuracy on the task. Even if when the heat map does not localize really well, human can achieve high accuracy and vice versa. So the correlation is pretty low, almost no correlation. So the second result we found is that if you provide the nearest neighbors, it will provide extra information. For example, if I ask you, is this an African hunting dog? The model thinks so. Do you say yes or no? If I provide you with these three heat maps, it's really hard to say. But if you provide, this is what the nearest neighbor returned to you. So based on this, you can see that this is kind of a pointy head dogs, and you can accept it. So the heat maps often highlight the main objects regardless of whether AI is wrong or right. and you have no ideas. But if you provide the nearest neighbor, it provides like supporting evidence, like all the way back to SVM, where you provide the support points. It actually make human help human make better decision. Like human can predict this is a caldron based on this, but not using these 3 heat maps. The quantitative method shows that showing nearest neighbor, the green is almost always in every setting better than showing the heat maps. So if I ask you, this is the model predict this is a caldron, and these are the example grouchus from the caldron. So do you think this is a caldron? The query. Yes or no? Large pot for boiling. Any attempt? Yes. So if you say yes, then you're right. Now there's a second question here. The model predict this is olive-sided flycatcher, and these are the example of this bird. So do you think this is olive-sided flycatcher? Yeah, so usually people also tend to say yes, that's what we found as well, but that's wrong because of the confirmation bias. Why? Because when the examples are so close, you tend to say yes because they're so close. So how do you help in this problem, right? So this is our method is come to the rescue, where we actually trying to show what the model is looking at when it does the comparison. So in this case, the 5 patch.
I'm trying to understand what it is that we miss coming under the law.
Oh, yes. You mean how? Yeah. So basically, this bird is not the same as these birds, different types.
Yeah.
They're different flycatcher, but there are many 5-grained ones that are looking so similar.
The reason I asked that question is that means we like to think that your AI algorithm is trying to capture what humans are able to do with one way. And over here, there's some aspect of this comparison that humans miss. And somehow the AI algorithm picked up. So that could be quite important. How is the AI algorithm seeing the image differently from humans that might give you some identity, some sort of insight as to how to classify images? So that's what I'm trying to get to this point. What is it that the AI algorithm is seeing that humans are not? What aspect of the image? We know that humans are wrong, but we haven't identified what aspect of the image that's drawing.
That's really interesting. It depends on which AI you're asking. If you're asking a CNN, you basically have no idea. We just know that if you train it on 5-grain classification, you will use a texture most of the time, but not the shape to make prediction. But that's why we need the explainable AI, where you can actually go in and see, oh, this is how the model does the comparison. Yes.
So the human was asked whether this is a flycatcher.
Yes.
It was not a flycatcher.
So the flycatcher is basically a longer bird. This bird is longer bird than this one. This one is shorter. So from different viewpoint, you cannot see it. And there's limited information. This is pretty much like face ID, where there are so many faces that are so similar. If you just rely on the whole image alone.
If you apply your patchwork algorithm to this, you have picked up relevant patches that were ID correlated.
Yes, exactly. So I think I have 6 minutes, so I will fast forward. It actually helps. So if you only use the nearest neighbor, actually hurt the performance. This is showing 3 random images from the grid class. The human can score 65% accuracy, and 50% is the random chance. It only saw 65. To provide nearest example, it actually go down. However, if you use the patch-wise explanation, where you first give a query, and then give it this, and then you ask the model whether this is, yes or no decision. This is on Gorilla, and then the human consistently we try to compare the algorithm AI improves accuracy over the nearest neighbor and also over the baseline. So consistently, human can use this, and this is no shared thing. It's just sometimes it will draw the wrong correspondence, but most of the time it's correct.
So this tool may be reserved for the next thing. So maybe we have to find it.
Yes. I'm already done. So my part 3, which is I save it to be a kind of a visionary slide where I do not show the existing work because it's ongoing and it's out of scope of the time of the talk. But one thing we're working on is, for example, first you ask the human or even the AI to come up with a set of patches to make decision, right? So typically, if you ask this, it will classify into in this case specifically, it will classify into this bird. Some are a tanager, but if you are a bird expert, you will know that this is a cardinal, right? So these 3 patches look like these 3 patches exactly, so nothing is wrong. But only the decision is wrong. The comparison is fine. So now, if you let a human intervene and then choose, and let's look at the beak, because the beak of that guy is red, the beak of that guy is red, and the first time is black. So now, if you ask it, the model will look at the beak and try to compare beak to beak, then head to make. So now the model actually arrive at the correct prediction, and you can try this demo online at our Auburn server. One thing I want to do in the future is that build the XAI that can process text and then find the supporting evidence from the internet so that it comes back and then inform the vision model. This requires the clip kind of multimodal in the process. Also requires a way to do retrieval naturally in the text alone. Yes, so we're working toward this direction. So in general, the existing AI and XAI is like a huge black box where humans try very different ways to do post-talk, trying to come up with some explanation out of it in one way. But my approach to the XAI is the following, where you have to enforce some low-dimensional bottleneck there, such that you can do two-way communication. The first is you understand, extract the rules out to this way. Second is you can debug and audit the rules. And the third one is you can edit the rules of going backwards, so you can change the model outputs. If you can interact with the model in this two-way approach, you can improve both trust and also, I think, accuracy for the human AI team. And a lot of works presented here is supported by NASA, NSF, NAVCare, Adobe Research. And thank you very much. So I have 2 minutes, so I will briefly tell you about my course in an outreach. So at Auburn, I have been teaching machine learning, deep learning, explainable AI, and theory of computation. I look at the UCF elective list, and I see algorithm of machine learning, AI, advanced AI, NLP that I can teach. And in outreach, I have run 1 year of K-6 AI club where we have like 30 kids come and then do AI, actual AI, training the model, but using Scratch, so it's really fun. I hope to continue that here at UCF, and thank you very much.
A very general question, here I'm using the neighbor, and this idea kind of like the transformer definition, right?
Yes.
You do everything. I know you already use contingent, but however, like for me, we can fully use that condition to instead of using the nearest neighbor, right? Because attention also build up, relation between different patches.
Right.
Is that possible?
So I think yes, we actually also have a subsequent work explore attention. With attention, you would need like 2 different branches, and then
more complex.
And then you have to train the model to do, the attention, and you cannot retrain it. Because once it learns how to compare in the transformer, once you learn how to compare, you have to use on the same input data. But in this case, the same algorithm actually works on ImageNet or birds. We don't need to do anything. But the transformer, you will need to retrain the model. You cannot use the same on ImageNet also for birds, because the way it compares is different.
Okay, that's good.
Yes. but it will be faster. It will be faster than this approach.
Thank you very much.
Yes, thank you. Just stop the recording.
It was very good talk.
Yes.
Nice.
Thank you very much.
Can I talk to you?
Sure. Let me log out from this.
Don't you worry, a long time no see. Okay. How are you?